Hello everyone, good morning. Today we will finish our discussion on the introduction of number theory, and then let's quickly go through the interesting topics inside. Give me a second, sorry. So I forget to to put a sign on my office so that nobody is going to disturb the class. Give me a moment, sorry. Great. Okay, so let's resume the class. So we will first talk about this modular arithmetic. So Gauss, in his book, a famous book, uh, I don't know how to pronounce it. Okay, this book, he gave the definition of important operation called congruence, which is the relationship of two integers. Here we say that an integer a is congruent, so it's like the same as b. Under the discussion about n, modulo n, if n divides properly the difference of a and b. So if this is the case, we can use the following notation to denote their relationship. We will say a is equal to or congruent to or equivalent to b under the word division by n, modulo n. So for instance, 29 and 15, they are the same under the modulo 7 operation. So in the world, when we talk about division by 7, 29 and 15 will be considered as the same. So in that sense, actually, 29, when it is divided by 7, it will have a remainder of 1. And similarly, 15, when divided by 7, it also will give a remainder of 1. So this congruence relationship actually is about the remainder operation. But in other words, or in the original definition here, this is actually an equivalent definition. We will see that 7 divides the difference of the two numbers, 29 and 15. So congruence relationship is actually an equivalence relation. So that's why it can represent something that is about equal. We can talk about equality between the numbers. So how do we check whether a relation is an equivalent relation? So whenever it satisfies three properties, then it will be an equivalent relation. I hope you can still recall something that we have studied in the undergraduate discrete math classes. So the three properties are, first of all, it is going to be reflexive. It means that for any number a, it is related to itself by the relation. So a is actually equal to a under modulo n. It is because n divides 0. Okay, so this is called a reflexive operation, reflexive property. And the other one is called a symmetric property. So symmetric property says if a is related to b, then b has to be related to a. Now, if we check the congruence operation, it turns out that suppose we know a is equivalent or a is congruent to b modulo n, then we also know that b will be congruent to a modulo n. The reason is that n divides the difference of a and b, so it means that n divides the difference of b and a. Is that okay? So it means that the congruence relationship is also a symmetric relation. Now finally, to check whether a relation is an equivalent relation, then we also want to have the transitive property. The transitive says that suppose that A is related to B, B is related to C, then we must have A is related to C. Now, translating in the congruence relation, so we want to check if we know A is congruent to B, and we also know that B is congruent to C, whether A is congruent to C. Now, it's true, yeah, because n divides the difference of A and B, n divides the difference of B and C. So n will divide the sum of the differences of a and b and b and c. So it's the sum of the differences of a and b and b and c. It will be the differences between a and c. So that's why we will have a is congruent to c modulo n. Okay. Now, because we have seen that congruence relationship is an equivalence relation, then it naturally will divide or partition the integers into different classes. So each class will basically have the same remainder under division by n. Okay. So here, this is giving us the exact relationship. A will be in the same class, or A is congruent to A when we, so A rem n means that this is the remainder of A under division by n. Okay. So the first one says that A, no matter how large the number A it is, it will be congruent to its remainder when divided by n. So A is congruent to A rem n. And the other one says that if A and B, they are congruent, if they are the same, then they will have the same remainder after division by n. So to prove this is actually simple. So you can go through this by the definition. And what is more interesting is about these facts. So it turns out that this congruence operator is really similar to the equality operator in arithmetic in most of the cases. So first of all, suppose that we know that A is congruent to B, then it is also true that when we add both sides by the same number, let's say C, they are still remaining to be congruent. So it is like if I add a number to A and add the same number to B, then it doesn't change the congruence relationship. So addition is allowed. The next one is, suppose that I know that A and B, they are congruent. Then by multiplying both sides by the same integer, let's say C, then it is still remaining to be congruent. So it is just like the equal sign in arithmetic. So multiplication is also allowed. And the next one is, suppose that we know A and B are the same, C and D are the same, then in that case we can do addition. On the left hand side will be the same as addition on the right hand side. So we will have A plus C is the same as B plus D. Now notice that when we have this plus plus or whatever, so we will need to be talking about the same modulo arithmetic. So we'll be talking about modulo of the same number n. Okay, it doesn't make sense when we talk about modulo n here and then we modulo another number, let's say k here. So everything is talked about when we are talking about in the world of division by n. So the third one talks about that we can use the natural way of adding the left hand side is equal to adding the right hand side. And lastly, we have also multiplication. So A is equal to B or equivalent to B, and then C is also equivalent to D. Then in that case, we can multiply the left hand side and multiply the right hand side, and the equality still remains to be the true. Okay. So these are something that is very useful in simplifying a lot of our calculation later. Okay, so we can have addition, we can also have multiplication. Now, we can also have subtraction. So for instance, if I know A is the same as B, then A minus C will be the same as B minus C, because minus C, so yeah, because we are just adding a negative number, it's still true. We can also do multiplication, but then we cannot do division normally. So for instance, suppose that we are using modulo 10 as our discussion here. We find out that 14 and 4, they are the same modulo 10. Yeah, because after division by 10, they will have the same remainder 4. And now 14 and 4, they are both an even number. Let's try divide the both sides by 2. So dividing on the left, we get 7. Dividing on the right, we get 2. But somehow we find that 7 will not be equal to 2 anymore if we still talk about modulo 10. So why is that not okay? Yeah, because it's not implied. So we just have addition. We just have multiplication. We can also have subtraction because subtraction and addition are still okay. Adding a number, minusing a number means adding a negative number. But then dividing an integer may not be equal to multiplying some other integer, right? So because we talk about integers here, we don't have any fractions here. So in that sense, we do not have division to be true normally, except what we are going to see next is for one special case, then we can be safe to apply division. So the case is like this, okay? Suppose that we know that b and n, they do not have any common factor. So GCD of b and n is equal to 1. So b is number. B is a number. We call it co-prime with n. Now, for a number that is co-prime with n, then it would be good when we talk about modulo operation of n. Suppose that we know BC is equivalent to BD modulo n, and also B itself has no relationship with n. Then in that case, we can divide both sides by B. So this is the case that we can do division. But we do not call this a division. Okay, we do not call this a division, but then it looks like a division. Okay, so how do we prove? Yeah, you can trace back the proof here, but then there are two ways of proving this. One is we apply a lemma that we have proven previously, or we can have another way to see why this is true based on the definition of GCD or the property of GCD. Now, GCD of Bn is equal to 1. What does that mean? GCD of Bn is equal to 1. It means that there exists a linear combination of B and n, which becomes 1. So we can find some B prime, multiply with B, and some Q, multiply with n, such that it is equal to 1. Okay? So B prime times B and 1 will have the same remainder when we are doing division by n, right? When we divide it by n, the remainder on the left-hand side will be B prime B. The remainder on the right-hand side will be 1. So B prime B is equal to 1 modulo n. Now, if this is the case, then what can we do? We know that for some B prime, after multiplying with B, it becomes 1 modulo n. So what we can do here is we have BC is equal to BD. We multiply B prime on both sides. This is allowed because multiplication is allowed. So we will have B prime BC is equivalent to B prime BD. And on the other hand, B prime B is the same as 1. So we can actually now replace B prime times B with 1. So we will have 1 times C is equal to 1 times D. So that means that we will have C is equivalent to D. Is that okay? So instead of viewing this as a division by B, we are thinking of this as multiplication of something called B prime here that makes B to go away to become 1. So we are multiplying the inverse of B. So the B prime here is called the multiplicative inverse. And then so it is better or more obviously to be written as B to the power minus 1. Yeah, because B to the power minus 1, when it is multiplied with B, we get a 1. Okay. Now, because of the previous result, we can have this following corollary. Suppose that P is a prime and K is not a multiple of P. Then 0 times K, 1 times K, 2 times K, up to P minus 1 times K, they will all have different remainder when we divide them by p. So if we take the remainder of them, they will form a permutation of the sequence of 0, 1, 2 up to p minus 1. So what does that mean? It means that exactly one of these numbers will have a remainder 0. Exactly one of these numbers will have a remainder 1, and so on and so forth. Moreover, because 0 times k is equal to 0, so we know that 0k, when divided by p, it will have a remainder 0. So this one will be this one. So it means that the latter p minus 1 numbers will have remainder being 1, 2, 3 up to p minus 1 in some special order. Okay? Yeah, the reason is that because each number there will be a so I will leave this for you to see why this is true. Okay, but this is something that is important to give us. So this to see why this is true, so you can prove this. But then this is an important intermediate result that allows us to prove a very interesting theorem called Fermat's little theorem. Okay, now suppose that p is a prime, then it says that for any integer a to the power p will have the same remainder as a under the division by p. So a to the power p is congruent to a. First of all, we separate the discussion into two parts. The first one is whether a is divisible by p or not. Now, if a itself is divisible by p, so p divides a properly, then a to the power p will be a multiple of p, so it will have remainder 0 when divided by p. And similarly, a will be divisible by p, so it will have a remainder 0. So in this case, if p divides a properly, then both of them are 0, so in that case it is true. On the other hand, if a is not divisible by p, then what do we see? In the previous corollary, we will see that a, 2a, 3a, up to p minus 1a, they will all have different remainder when we are dividing by p. So if I multiply them together, this product will have the same remainder as what? As p minus 1 factorial. Is that okay? Yeah, because one of them is going to be equivalent to 1, one of them is equivalent to 2, and so on and so forth. So for all these p minus 1 numbers, if I multiply them together under modulo arithmetic operation, they will be equivalent to the product of 1, 2, 3 up to p minus 1. So it is p minus 1 factorial. But on the other hand, a rem p to a rem p will have the same remainder as a times 2a times 3a times up to p minus 1a. So if we multiply all these numbers together, we will get a to the power p minus 1 multiplied with p minus 1 factorial. Okay? Now we have this one is the same as this one. What we can do next is we divide both sides by p minus 1 factorial. This can be done. It is because any number from 1 to p minus 1, they are coprime with p, so that we can apply the division operation. Divide both sides by p minus 1 factorial, we will get 1 is equivalent to a to the power p minus 1. And after that, we multiply both sides by a, then we get a to the power p is the same as a. So this part handles the case where p does not divide a, and this part handles the case where p divides a. Okay? So this is called Fermat's little theorem. And then we also have Wilson's theorem. So Wilson's theorem says that let's check the value m minus 1 factorial modulo m. So we have m minus 1 factorial, and then we divide it by m. And let's see the remainder. If the remainder is minus 1 or m minus 1, minus 1 here. Minus 1 and m minus 1 will be equivalent to each other, right? So if the remainder is m minus 1, then m is a prime. If the remainder is not m minus 1, then m is not a prime. So in that case, Wilson's theorem gives us a property about prime numbers. Whenever we have a prime number, then p minus 1 factorial will be equal to minus 1 modulo p. On the other hand, if a number m is not a prime number, then m minus 1 factorial will not be equal to minus 1 modulo n. So we can actually use Wilson's theorem to check whether a number is a prime or not. But unfortunately, the time it takes to perform m minus 1 factorial is linear to m, so which is exponential to log m. And so using Wilson's theorem to check whether a number is a prime requires exponential time. So it is not an efficient method to check for primarity, but then it is still an interesting property. So yeah, why is it true? Yeah, I will leave this for you to check the OCW recording. And then the next part is going one step further about modular arithmetic. We will define something called the Euler Phi function. Okay, so recall when AB has greatest common divisor to be 1, then we will say A is co-prime to B. Or we will say A and B, they are relatively prime. Now, Euler studied the following function, although at that time, Euler didn't use the notation phi to represent such a thing. So phi is a notation introduced by Gauss, but Euler is studying this first. Okay, so what is phi of an integer n? Okay, phi of an integer n is the number of positive integers less than or equal to n, such that the integer is coprime to n. So what does that mean? So phi of 1, we look at the numbers from 1 up to 1 and find how many of them they are coprime with 1. So phi 1 is equal to 1. How about phi 7? So we look at all the numbers from 1, 2, 3 up to 7. We want to count how many of them are coprime to 7. We will see that 1, 2, 3, 4, 5, 6, these 6 numbers are coprime to 7. But 7 itself is not, because 7 and 7, they will have a greatest common divisor 7, not equal to 1. So phi of 7 is equal to 6. How about phi of 9? So we claim that phi of 9 is equal to 6. The reason is that if we consider the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, we find that 3, 6, 9 will not be coprime with 9, but all the remaining numbers 1, 2, 4, 5, 7, 8, all these 6 numbers are coprime to 9. So in that case, we will have phi 9 is equal to 6, phi 10 is equal to 4. So this function is called Euler Phi function, or in the literature, people also call this the Euler totient function. So the meaning of totient just means that the number of positive integers at most n, which is coprime to n. Yeah, so it is totient. So this totient. So this is called the Euler Phi or Euler totient function. Okay, based on the definition of Euler's Phi function, we can generalize the Fermat-Little theorem as follows. Okay, so Fermat's Little theorem, so if you recall, okay, Fermat's Little theorem, the modulo thing here must be a prime number p here. So in Euler's extension, we will generalize this. It is no longer just for a prime p, okay? But before we talk about the generalization, yeah, so we will have an extension about this corollary. This time, suppose that we have a number k, which is coprime to n, and then we also let k1, k2 up to k phi n to be all the numbers between 1 and n such that they are coprime to n. So in that case, we have phi n of them. So let's call them k1, k2, k3 up to k phi n. We don't care about the ordering. That's okay. But then these are the distinct numbers that is coprime to n within 1 to n range. Then what do we see? We try to multiply each number by k. So we have k1, kk2, kk3 up to k times k phi n, we claim that all these numbers here remains to be coprime to n. Originally, k1 is coprime, k2 is coprime, k phi n is coprime, k itself is also coprime. And after doing the multiplication, they are still coprime. Yeah, it's actually quite easy to see. It is because of the unique prime factorization theorem. And what's more is that, okay, if we take the division by n, all these numbers will have different remainders. So all these numbers will be numbers coprime to n, and then the remainders are different. So that means what? That means that the remainder will be a permutation of k1, k2 up to k phi n. Okay, so why is it true? So it's simple. So I'll leave this for you. So this is just reapplying, the same proof. Yeah, so we are proving corollary one here. This is for the preparation of Fermat's little theorem. So the proof of corollary one will be extendable to the proof of corollary 2 here. Okay, and because of this time we can extend Fermat's little theorem for general case. This time we mod n. Instead of a to the power p is equal to a, we have k to the power phi n is equal to 1 modulo n. But then we have conditions. Okay, the k that we talk about here must be coprime with n for this to be true. So why do we call this a generalization of Fermat's little theorem? Let's imagine when n is equal to p, what will happen? Now, when n is equal to p, then phi of n will be the numbers between 1 to prime p, such that it is coprime with p, so it is exactly p minus 1. So it says that if a number k is coprime with the prime p, then k to the power p minus 1 is equal to 1. So this is what we have shown here. K to the power p minus 1 is equal to 1. So we have done this. So if this is true, then this handles the case for k coprime with n, with the prime p. And on the other hand, if it is not coprime with p, then we will always have k to the power p is equal to k, or k to the power p minus 1 is equal to 0. Okay? So this is the Euler's extension of Fermat's little theorem. Okay? And then the Euler Phi function can be expressed as phi of n to be equal to n times a product of 1 minus 1 over p, where p are exactly those primes that can divide n properly. Okay, so why is it true? So I will leave this for you to check the OCW recording. But as an example, so let's try to find out what is phi of 10. So we have phi of 10 here to be 4, right? So phi of 10 to be 4, so why is it true? So first of all, let's apply this formula. Phi of 10, so it is equal to 10 multiplied with something. So we want to find out what kind of prime numbers will divide 10 properly. So 2 is a possible prime, and 5 is also a possible prime. So in that case, phi of 10 will be equal to 10 times 1 minus 1 over 2 times 1 minus 1 over 5. And after doing some simplification or calculation, we will get it is equal to 4. So this is a formula that allows us to compute phi of n easily when we know all the distinct prime factors that divide n properly. Okay? And also, phi n is also what we call the multiplicative function. It satisfies this interesting behavior. So suppose that we can factorize n into the unique prime factorization. So it is p1 to the power e1, p2 to the power e2, up to pj to the power ej. Then phi of n can be computed by taking the phi of each individual part. Phi of P1 E1 multiplied with phi of P2 E2 up to phi of Pj Ej. Or, in general, as long as A and B, they are relatively prime, as long as A and B, they do not share any prime factor, phi of AB is equal to phi of A times phi of B. Okay, so this is something that allows us to compute phi very quickly. And one more, I think there is a useful formula for us. Okay, so why is it good? Yeah, let's take a look of this one. What is phi of P1 E1? So imagine, what is phi of 3 to the power 4? 3 to the power 4 is 81, right? Right? So phi of 3 to the power 4 is simply because 3 is the only prime factor that divides 3 to the power 4. We can now use this formula. Phi of 3 to the power 4 is simply 3 to the power 4 multiplied with 1 minus 1 over 3. So we can calculate this very easily. Alternatively, if it is about 3 to the power 4, so what are the numbers between 1 to 3 to the power 4? That is not coprime. Not coprime, they are exactly those multiples of 3. So we cancel, we take away those not coprime, then we get the coprime part. Yeah, so that means that whenever we can have the prime factorization of integer n, then we can calculate the Euler Phi value of n very easily. Okay. Okay, so this is the slides 12 and slides 9. Okay, so let's take a look of the next set of slides. We will talk about application of this Euler Phi function. Okay, so in particular, we will talk about a crypto system for sending message to your friend secretly called RSA. So what is meant by a crypto system? A crypto system allows a sender to send a message, let's call it M for message, in some form, let's call it C. C is some crypted message. It is some encoded so that people do not understand. So we call it a C, such that any receiver that is intended to receive the message can decrypt the message, but on the other hand, anyone that is not the intended receiver cannot understand what the message in the crypto form is. Okay, and then a lot of crypto systems, they are symmetric in the sense that sender and receiver will share a certain secret, and then they use this shared secret to make the message. But there could be a problem about sharing the secret. So usually, how can a secret key be shared? Usually, a secret key be shared by using what? So I meet you in a place in person, face to face, and then I pass you the secret. So this is one way. But then it is not that very easy, not very convenient. So in that sense, 3 mathematicians or computer scientists, one of them is called Rivest, one of them is Shamir, one of them is Edelman. So Rivest is one of the author of our Introduction to Algorithm textbook, CLRS. Okay, so Rivest, Shamir, and Edelman. So in 1977, they announced a certain scheme that allows us to do the encoding without shared secret. So people nowadays call this crypto system or this method the RSA Cryptosystem. But in fact, such a similar system was also designed in England earlier in 1973 by Ellis and Cox. But at that time, this is really secret. They use it in the military intelligence, so that this scheme was not announced at that time. Okay, this kind of system, they do not need to have secret sharing of a key, so we call this a public key crypto system. Okay, so how does this work? Okay, so this is the purpose of today's lecture. So So to apply this RSA Cryptosystem, we need to do some preparation first. We call this a setup phase. Okay. So setup phase, the receiver who wants to receive a message will do the following. So the receiver first choose two distinct primes P and Q, and then this P and Q, they are usually very large prime, and then make the product of PQ. So let's call it N. And then the receiver, because knows about PQ, so this one must be able to compute phi of n very easily. Phi of n is simply p minus 1 times q minus 1 using our formula. And we know phi of n, then we can easily find an integer e such that it is coprime to phi of n. Yeah, we just make a trial and error so that we can get some integer e that is coprime with phi of n. And then the two special number e and n will be called the public key. And this e and n can be announced to everyone, any person who wants to send a message to me. And then for the receiver who is designing this n and e, he or she can find a unique d such that ed is equivalent to 1 modulo phi n. Now the reason is that, this d, assuming that it is between a value of 1 and phi n, okay? So we have ed. The reason is that because e and phi n, they are coprime, so that means that their greatest common divisor is equal to 1, so that means that there is a certain inverse that can multiply with e to be equal to 1, so let's call d to be the inverse. And then the receiver will keep d and n, these two numbers, secretly, so he will not announce this to the public. Everyone who wants to send a message knows about e and n, but only the one who is going to receive the message knows about this value of d. Okay? Once this is done, then the encryption process, making a message into a crypted code, is easy. A sender will know what is the value of e and n from the receiver, so when he has a message to send, let's say the message m is an integer between 0 and n, what he wants to do is simply make the power, we make m to the power e, and then divide it by n and get the remainder. So the crypted message C will simply be equal to m to the power e modulo n. Okay, is that okay? Taking the remainder. So the sender will send C, this crypted message, instead of the original message m, to the receiver. Now anyone can see about this C, but then getting the value of C, knowing the value of e and n, is really hard to find out the original message m. We just have m to the power e. We know that C is equal to m to the power e, but we know nothing. There is no way that we can easily do log of m, right, to a number. So in that case, the C can be sent through some, an unsafe channel to the receiver, but then there is no worry about someone who can understand what is the original message m to be. But on the other hand, how can a receiver recover the original message? The idea here is simple. The sender gives C to the receiver, so the receiver takes C and do some similar steps. This time, she raises C to the power of D, so we get C to the power D. Then C to the power D will become the original message M. So the scheme is very easy. So why is it true? Okay, so we need to show something. Okay, at least we need to show that the decryption of RSA works for any message M. Let's take a look of two separate cases. When M is coprime to N, what will happen? Okay, now when M is coprime to to n, then we are actually using the Euler's extension of Fermat's-Little theorem. So let's compute c to the power d. We want to find out that c to the power d is exactly equal to m. So why is it true? So c to the power d turns out to be the same as m to the power e to the power d, because c is m to the power e. Now what is ed? Ed itself is a multiple of phi n plus 1. This is by the choice of E and D, right? So D is the multiplicative inverse of E modulo phi n. Now, so in that case, we can replace ED as 1 plus some number, some integer multiplied with phi n. On the other hand, m to the power 1 plus t phi n is equal to m to the power 1 multiplied with m to the power t phi n, but m to the power phi n is 1 using Fermat's the extension of Fermat's-Little theorem, because m itself is coprime to n. So in such a case, m to the power 1 plus t phi n is m to the power 1 multiplied with 1, which is equal to m. So what does that say? It says that c to the power d and m will be the same under modulo n, and because these numbers, they are assumed to be between 0 and n minus 1, so in that case, it is uniquely decoded, so m must be equal to this one. Now, this handles a particular case when m is coprime to n. Then we can do something that is similar. So I will leave this for you to check. So we have actually 3 more cases to consider. One is m is divisible by p but not by q. Recall that n is a what? N is a product of 2 primes. So one case is m is a multiple of p but not q. And then the other case is m is a multiple of q but not p. And finally, m is both a multiple of p and q. So in any case, then we will also see that m can be uniquely recovered. And so that's why RSA cryptosystem work. So it says that it works in the sense that the receiver can trace back the original message. But why is this safe? Okay, so we have an example. So you can go through this later, and then there is actually an assignment question for you to test your understanding. Okay, now in the remaining set of slides, so we have pointed out some security issues of RSA. So why is RSA considered to be safe now, and what is what is the reason? And then if the reason or is no longer true, then in that case RSA will break down. So this part will not appear in the exam, so don't worry. So we will make this so for your own interest. Okay, I think that's all for today's lecture summary. Let me check if you have any questions. Yeah, if you know, then then we have the assignment 5 ready for you to try, and then the deadline is next Monday and before midnight. And then for next week, perhaps I will talk about something that is interesting. I will talk about the Chinese remainder theorem, which is also a related topic, okay, to this number theory. Okay, that's all for today. Thanks. Thank you.